I wanted to go over this example with you because it shows a neat little trick. Now, in this problem, we're supposed to find the points on the sphere that are closest and farthest from the point 3, 1, -1. So we want to optimize. What are we trying to optimize? We're trying to optimize distance. And it is subject to the constraint of being on that sphere. So it is distance from the point 3, 1, -1, subject to the constraint being on that sphere. Okay, so our formula, let's see here. So we would say distance between x, y, and z. This is going to be our formula is d. So it's going to be the square root of x minus 3, quantity squared, plus y minus 1, quantity squared, plus z plus 1, quantity squared. And the constraint, let's put it g of x, y, z, is going to be x squared plus y squared plus z squared equals 4. Here's the trick. The trick is whenever you were minimizing or maximizing distance, instead of using the distance formula, you can do your analysis with the distance formula squared. Okay? And the reason why is because if you look at it like this, so you've now got d squared is equal to, right, the blah, blah, blah squared plus blah, blah, blah squared plus blah, blah, blah squared. So now if I'm going to take my partials, I'll have 2d dx or 2d dy, 2d dz equals blah, 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 right? So when you divide, everything is being divided by the same factor. So when you're maximizing, you end up having the same critical values. Okay. The only thing is you're just in that gradient, you're scaling by a factor, by the same factor. Okay, so that's the thing to remember, is that you just want to use the square of the distance whenever you are optimizing distance. Okay, so now let's do that. So if we do this, now what is our gradient? So the gradient of d is going to be, it'll be 2 times x minus 3, 2 times y minus 1, comma, 2 times z plus 1. Okay, and the gradient for g is going to be 2x, 2y, 2z. Okay, so when we go to solve, partial of d is equal to lambda times the partial of g. That becomes 2 times x minus 3 equals lambda times 2x. 2 times y minus 3 equals lambda times 2y. 2 times z minus 3 equals lambda times 2z. Okay? And again, remember we've got it subject to the constraint of g equals 4. So add to this x squared plus y squared plus z squared equals 4. Okay, so what can we do? Well, one of the things we can do is we can just write here. So from this first equation here, we get that x, so let's see here, 2x minus 6 minus 2 lambda x equals 0. Okay. Oh, I don't like that. Let's see here. So if I have 2 times x minus 3 minus 2 times lambda x equals 0, divide by 2. So now it's x minus 3 minus lambda x equals 0. And x times 1 minus lambda is equal to 3. So then x is now equal to 3 over 1 minus lambda. And we can do the same thing for y. So the same thing will be true for y. So 2 times y minus 3 equals lambda 2y. We'll get the same thing, that y is equal to 3 over 1 minus lambda. And lastly, for z, how do I have exactly the same thing? So it should be x minus 3, it should be y minus 1, and z plus 1. Y minus 1, z plus 1. So change this to minus 1. So up here should be a 1. And then for the z, we should get z plus 1. So it should be z equals negative 1 over 1 minus lambda. Okay. And so now that we've got that, let's just verify, though, as we do this, can lambda equal 1? Because if lambda equals 1, we cannot actually divide by 1 minus lambda. That would be dividing by 0. And the answer is, well, if lambda is equal to 1, then that's impossible because you'd have 2x minus 6 equals 2x. So you'd have negative 6 equals 0. Right, so 2 times x minus 3 equals lambda times 2x. So you'd have 2x minus 6 equals 2x. So you'd have negative 6 equals 0. Contradiction. Right? So this is all okay. So now we've got x, y, and z. And what we're going to do is we are just going to plug them in to our last equation right here. So let's call this equation number 4. So we've got our constraint here. So x squared plus y squared plus z squared equals 4. X is 3 over 1 minus lambda. So that's squared plus y, 1 over 1 minus lambda. And then plus z, which is negative 1 over 1 minus lambda, quantity squared, equals 4. So we'll get 9 plus 1 over 1 minus lambda squared equals 4. So 1 minus lambda squared is equal to 11 over 4. And this is perfect for solving. We can use our quadratic, right? So be lambda squared. What is that? 1 minus 2 lambda. So minus 2 lambda plus 1 minus lambda over 11 over 4 equals 0. Right? So you solve that and you get lambda equals plus or minus. Actually, we can solve it. You don't have to use quadratic formula. So we could get that 1 minus lambda equals plus and minus square root of 11 over 2. So then lambda equals 1 plus or minus square root of 11 over 2. Okay, and now you would take this value of lambda and plug it back in to get x, y, and z, right? So x is equal to 3 over 1 minus. Now for your values of lambda, you've got 1 plus square root of 11 over 2, right? Or 3 over 1 minus, 1. It's got to be 1 minus lambda, so it'll be 1 minus square root of 11 over 2, etc., etc. Right, so you get some points for x, y, z. And the corresponding points are 6 over square root of 11, 2 over square root of 11, negative 2 over square root of 11, or negative 6 over square root of 11, negative 2 over square root of 11, 2 over square root of 11. Okay. So now the last thing we've got to do is we've got to plug in and see which values give the larger value of x and which give the smaller value of x. Right, so find the points on the sphere that are closest and farthest. So you would plug in for our d, right? So the distance is, remember, it's like x minus 3 squared plus y minus 1 squared plus z plus 1 squared. You would do that, plug them in, and it turns out that this is going to give you the smallest value. So this is closest to the point 3 comma 1 comma negative 1. And this one is farthest. Okay, so the thing to remember really about this example is whenever you are analyzing distance, you can save a lot of energy and time by just using the square of distance as your optimizing function.